All right, 7.2 radioactive decay. So last lesson, 7.1, was mostly review, but it was important to set the stage for what we're going to see next. And especially what we talked about with isotopes is going to be important in this lesson. So first off, we're talking about radioactivity, and that is when the nucleus of an atom spontaneously disintegrates. Spontaneously disintegrates. Okay, and if you don't know what those words mean, it just means that it suddenly splits apart into smaller pieces. And so that's what's happening. Radioactivity means that our nucleus is unstable and it splits into different nuclei. It actually changes into a different element. And so we have unstable atoms and stable atoms. What makes an atom stable is when the strong nuclear force, which is the force that binds all the neutrons and protons together in the nucleus. It's what holds them all together. That's one of our four fundamental forces. The strong nuclear force, when that equals our electrostatic force, when that is equal to the force that the protons are pushing away at each other with, you know that if you have two protons near each other, they're going to push away because they're both positive. And positive, like charges, will repel each other. So the protons are pushing each other away, the strong nuclear force is pulling them back together again, and the atom is stable when those two are equal, when they're balanced. And they're unstable when they're not balanced anymore. Now, atomic number, the higher atomic numbers we have, as you go up the periodic table, you get more protons. Right? A higher atomic number means it has more protons. And if it has more protons, that means it has more electrostatic force. And if it has more electrostatic force, that means that it's less stable. So that's why you see, as you go up the periodic table, you start to see elements that are very rare to actually see in the real world because they decay so quickly. And things like plutonium and uranium, all high up on the periodic table because they decay a lot. These are great for nuclear reactors, these sorts of elements. Okay, so we have three types of decay, three ways that our nucleus can split apart into different ones. The first one is alpha decay. That we use this Greek letter alpha. It looks kind of like a fish, or a bit like the letter A. Okay, number two is beta decay. And again, that's a Greek letter. It looks like a bee with sort of a funny hook on the front. And number three is gamma decay. And that is also a Greek letter. It looks like this. Those are our three types of decay, alpha, beta, and gamma. And those are the Greek letters that correspond to A, B, C. It's the first three letters of the Greek alphabet. So our first type of decay, alpha decay. Well, what is alpha decay? That's when the nucleus emits an alpha particle. And maybe that's not very helpful because you don't know what an alpha particle is. So that's our next line here, an alpha particle. An alpha particle is two protons plus two neutrons. And that might look familiar to you, two protons and two neutrons. Well, that's just equal to helium. 2,4 helium. And that's what it is. So an alpha particle is just a helium particle. In the picture to the right here, you can see we've got two protons and two neutrons, which is our helium particle, being shot off away from the plutonium. So this is an example here. Plutonium often undergoes alpha decay. And so what it is we have plutonium here, which has 94 protons and 146 neutrons. You can see that at the bottom there. and it loses it loses an alpha particle. So it shoots off 2 protons and 2 neutrons, which means that 94 goes down to 92, and so 94 goes down to 92, 146 goes down to 144, because it's lost 2 of each. Now, if our protons goes down from 94 to 92, we have a new element. It's not plutonium anymore. It's become uranium. Uranium is the element with 92 protons. And so you can see that in this process, the plutonium changed into uranium by shooting off an alpha particle. So that's alpha decay. We've got the example here. We're going to write the equation for that. So it looks like this. Plutonium is 94, and we said that this plutonium has a mass of 240. We've said plutonium 240. So we have 240, 94 plutonium, and that converts into 92, 236 uranium. You can see that the protons went down by 2, the mass went down by 4 because we have protons and neutrons. Okay, and we have our 4,2 helium being shot off. And that looks a lot like a chemical equation. You might recognize that from chemistry. Except in chemistry we're dealing with molecules, we're dealing with substances that combine multiple elements. But usually your elements themselves don't change. Here we've got plutonium changing into 2 completely new elements. So this is not chemistry, this is physics, this is nuclear physics here. Alright, now we have a general sort of pattern for that. We say that when something undergoes alpha decay, if it has an atomic number of Z and a mass number of A, and we'll call it X. Oops, I'm just writing that a bit too large, so I'm just going to make that a bit smaller here. So ZAX, like our plutonium there, it converts into, well, at the bottom here we have Z minus 2, A minus 4. It's going to give us Y, some Y element, plus our 2,4 helium. This is our alpha decay. And in this equation, we call X the parent atom. And we call Y the daughter atom. All right. So we've got a problem here that we can work through. It says when lead-204 undergoes alpha decay, it produces a stable isotope. We want to determine the element and its atomic number and mass number, and then write down the nuclear reaction equation. So to start off with, we have our lead-204. Now first thing is to find lead on our periodic table. So I'm going to do that. I'm going to open up my periodic table here, and I'm going to find lead. And if you see, it's over 82, sort of in the bottom right area. It says PB lead. Okay, so 82. So that means we've got 82 PB, and its mass was 204. That's what the problem told us. Okay, it's going alpha decay, so it means that the 82, we're going to do 82 minus 2 here, 204 minus 4. So 82 minus 2, well, we'll just call this, again, our daughter atom. We don't know what it is yet. It's Y. Some unknown thing. Plus 2,4 helium. Okay, so we want to figure out what Y is. 82 minus 2, this was 80. 204 minus 4, that's 200. We have 80 protons on this thing. That's the atomic number. So we need to look up, again, over here, 80. 80 is Hg mercury. So we call this one Hg, and that's what we're working with here, 280 Hg. So to answer the question, because it asks for a few pieces of information, it asks us what's the element. So the element is mercury. It asked what is the atomic number. And that is 80. And it asked, what is the mass number? Well, the mass number is 200. The last thing it asks for is the nuclear reaction equation. So we have 82,204 PB. This is basically what we wrote at the top, but now we're going to fill in what that missing one actually was. 80, 200 Hg plus our 24 He. And there's our complete answer. Notice that the question asked a few pieces of information. Cool, so that is our alpha decay. We've got two other types of decay. This next one, beta decay, is actually has a few different types of beta decay. So, so yeah, we're going to look at a few interesting things here. Beta decay is when a beta particle, we'll say a beta particle, is released or absorbed. So it's a bit different from alpha. Alpha, we only released alpha particles. Beta, we can actually absorb beta particles. What is a beta particle? Well, it is an electron and we call an electron -10 because it has basically a mass of 0, but it has a charge of -1. Okay, so electron, or a beta particle can also be a positron. Now we haven't met positrons yet, but positrons, they're exactly like an electron, except they have a positive charge instead of a negative charge. But they're basically just an electron with positive charge. That's all it is. So they're very light. You see that the mass number is still 0. The only difference is that we have positive instead of negative. And positrons you don't see too often, but they do exist. They're a real thing that are out there. They're just not very common. Okay. So, beta negative decay. We've got three types of beta decay. The first one here is beta negative, second one is beta positive, and the third one is electron capture. So we're going to start with beta negative decay, and this is when an electron is emitted. Okay, that is our beta negative decay, and our equation for that, it looks something like ZAX to Z plus 1 AY plus -1 0 electron. And notice that, I mean, just if you know that you're shooting off an electron, well, that's a -1. So it means that the Y particle, the Y element here, needs to have an atomic number of 1 more. Right? If our because it needs to all balance out. You see that the numbers balance out. A on the left is equal to A on the right. Z on the left is equal to Z plus 1 minus 1 on the right. So it all balances out. All right, there's a picture to the right of an example of our beta negative decay. So we have an electron being shot off, and it creates a new particle. So the example here is tritium H3. So remember we talked about tritium in the last lesson. So the equation would look something like this. We have 1, 3 hydrogen. Remember tritium has a mass number of 3. Okay, and that becomes 2, 3 helium plus -1 0 electron. That's an example. All right, we also have beta positive decay. This is where a positron is emitted. All right, we have again an equation for this. We've got ZAX goes to, in this case it's going to be Z minus 1 because we're losing a positron. Y plus 1 0 E. That's our positron. And so an example of this is our carbon-11 decay. This is a thing that happens in nature. So carbon-11, 611 carbon to 511 boron plus our +1 0 positron. Alrighty. Now there's one more type of beta decay, which is electron capture. Now, so just for the record here, you do need to know these three types of decay. You need to have an idea of what they are and what they mean. Your alpha, beta, and gamma decay. Hopefully the homework will give you some practice with what those are and what they mean. But you need to know that alpha, you need to know what an alpha particle is, you need to know what a beta particle is, and you're going to need to know what a gamma ray is, which is the last one. Alright, so just finish up here, electron capture. Instead of releasing an electron or releasing a positron, now we're actually absorbing an electron. So this is where an electron is absorbed. Electron is absorbed. And our equation for that, well, we're gaining electrons. So we have ZAX, and we're gaining an electron, so we've got plus -1, 0, E. And then you can just do the math. We've got Z minus 1, and A hasn't changed. Why? There we go. And our example is nickel 56. Nickel 56 looks like this. Okay, so we're gaining an electron, which brings us down to cobalt. And the mass hasn't changed. Cobalt. Okay, that's our beta decay. Next page. Next page you'll see we have one little problem that we can do to try solving here. We have our 83 214 bismuth. I found the 83 from the periodic table as well. So it says, when bismuth 214 undergoes beta negative decay, beta negative, that means it's losing an electron. So when it does this, it produces a stable isotope. We want to determine the element, atomic number, mass number, nuclear equation. So we have bismuth. Well, we're going to be losing an electron, so that means the mass number goes up by 1. So we have 84, 214, and if you look in your periodic table, that gets you polonium. Plus -1, 0 electron. And let's see, that's our equation. We want the atomic number. Here's our atomic number is 84. Our mass number is 214. And the name was polonium. There we go. All right, gamma decay. So gamma decay is, just like the other ones, is where it's going to involve a gamma particle, right? Well, it's actually not quite a gamma particle. This is a gamma ray. In this case, a gamma ray is released. So we say a gamma ray because a gamma ray is just light. And we're not talking about it as a particle here, we're talking about it as a wave. So it's a bit of light that is emitted. And oops, I think you're going to have to ignore the picture that's on the right there, because this is not the right picture. I will fix that in your handout. Alright. So in your handout you should see you have a particle, an atom, and it just releases a photon. Or at least releases a gamma ray. So a gamma ray is light. Or a photon. Okay, and it's a very high energy light. We'll see a bit more what that means in a second. We have an example here of helium-3. So when we have helium-3, and I'm going to put a star here. And the star means that it's in an excited state. Okay, so I'm going to put that over here. Star is excited state. Okay, and we've got that just a couple lines down, so we'll explain what an excited state is in a second. So when you have helium and it's in an excited state, Well, it goes down to the same thing. It didn't change. It's still just helium, but you see I don't have the star anymore. And then I'm going to add a 0, 0 gamma ray. Okay, so all that's happening is I'm converting that star into a gamma ray. Notice that the gamma ray doesn't have any mass, it doesn't have any charge, it's 0, 0. So not much has changed. Okay, and our general equation for that is we can say if we have ZA x star, and that's when it's in an excited state, goes to ZA x not excited plus 0, 0 gamma. Okay, so I keep on saying excited state. What do I mean? Well, do you remember in the last lesson we talked about electrons and how they can be in different shells. They can bump up to a higher level if they want, and they're in this excited state for a while, and then they pop back down and they release a photon. That's what this is. So an excited state is where an electron is in a higher energy shell. And it just popped up there and it's going to pop back down. Okay, so that's our gamma decay. And we have a problem here. When dysprosium 152 undergoes gamma decay, its nucleus changes from an excited state to a stable state. We want to write the nuclear reaction equation for this gamma decay. Okay, well, the gamma decay, we've got our equation here. Dysprosium is 66, our mass is 152, dy star to the same thing, 66, 152 dy plus 0, 0 gamma. There you go. Okay, before we finish that bit, I wanted to say one thing. Actually, what I said about the excited state, I just realized it's not really true. That is one sort of excited state that can happen, electrons being at a higher energy level. But actually what we're talking about is in the nucleus. The electrons aren't in the nucleus. So this is when, just when the nucleus has extra energy. And we won't get into why it has that extra energy. We're just going to say that the nucleus has some extra energy, it wants to release it, and so it does that by releasing a gamma particle, or a gamma ray. Excellent. Okay, so we have one last little bit here. We've been talking about all these different types of radiation, and why should you care? Well, you probably know that radiation is bad for you. Radiation equals cancer, all these sorts of things, right? So why? Radiation is just, it's these particles, right? We just saw, so we've got a helium. Helium's not so bad, right? There's nothing wrong with helium. And we've got, the other one was just a single electron. Well, electrons aren't so bad, are they? And the last one was just a bit of light. Light isn't so bad. So why do I care about radiation? Why is it bad? Why is it giving me cancer? The answer is that all of those things didn't have, they were all ionized. The helium particle didn't have any electrons. The electron by itself is just an electron, so it has a charge. And the gamma ray doesn't actually have an electron involved, but it is transferring energy which can alter the electrons of other particles. It can strip away the electrons. So that's the problem here. The danger of radiation is that radiation can ionize, which means strip electrons from atoms. So it can strip these electrons away from atoms. If you have some radiation firing at you, you could be losing a bunch of your electrons off your atoms, and that's not good. That can cause burns, tumors, etc. All right. So in the end here, we're just going to summarize these different types of decay and say something about this penetrating ability. And I'll say what that means in a second. But for alpha decay, the radiation we had was an alpha particle, which was our 2,4-He. Okay, beta negative, we emitted a electron, which was -1, 0. Beta positive, we emitted a positron, which was +1, 0 E. And here we didn't actually emit anything here with electron capture. We gain an electron. Okay, we gain an electron there. And for gamma, we have our gamma ray, which is a photon with 0, 0 gamma. Good. Okay, so those are our different types of radiation. And we have electric charge. Well, 2,4 helium with no electrons, we've got 2 protons, no electrons, that has an electric charge of +2. Beta negative, charge of -1. Beta positive, charge of +1. Electron capture doesn't actually emit anything, so that's not so much of a problem. And gamma doesn't have an electric charge. Okay, so you can imagine that the alpha particles probably be worse for you because they have the largest electric charge. So if ionization is the problem, they can really do some bad things to electrons. But the last factor here is the penetrating ability. And alpha particles don't get very far. They can't penetrate through walls, for instance. Right? How far can they penetrate? Well, they can penetrate skin or paper. That's it. And it's slow. These alpha particles, they're slow. So if you want to protect yourself against that kind of radiation, just a single wall is going to be enough. Or like some sort of, you could definitely get a suit that's going to protect you from that. So that's not so much of a problem. I mean, it is a problem. If you're exposed to alpha radiation, that's very bad. But it's pretty easy to protect against. Beta negative, well, and beta positive, these guys both can penetrate how much? A few sheets of aluminum foil. Okay, that's how much those can penetrate. So that's a bit more. It's still reasonably easy to defend against. Electron capture, we're not actually emitting any radiation, so that one's not so bad. The last one here, gamma. Well, gamma is the worst one. It doesn't have as much electric charge, so it doesn't, each individual bit doesn't do too much, but it can get a lot farther. This can penetrate a few centimeters. A few centimeters of lead. Okay, and lead is very good protection, and so that's really when you have these big bunkers, these big fallout shelters that have these thick concrete walls or lead walls, that's to protect against gamma radiation, which really can seep into everything. If you're not safe just being in a building from gamma radiation. So those are the different types of radiation. Those are why they're important, and those are how it works. So do check out the homework. I think that you'll find it pretty interesting. Enjoy. Oh, and sorry for such a long lesson.